and this is my Physics 2 Lab 6 Magnetic Molasses presentation. So the purpose of this experiment is to investigate the effects of Faraday's law and electromagnetic induction by observing a bar magnet falling through a conductive aluminum foil tube. As the magnet moves through the tube, its changing magnetic field induces currents in the aluminum foil, which creates their own magnetic field that opposes the motion of the magnet according to Lenz's law. This interaction causes the magnet to fall more slowly than it would under gravity alone. Using a smartphone, bar magnet, aluminum foil roll, and a meter stick, in our case we use a ruler, the experiment measures the motion of the falling magnet, models the magnet tube interaction computationally, and compares the predicted results with the observed behavior to better understand the relationship between induced current, magnetic fields, and magnetic force. So some of the key physics principles that we see in this lab is Faraday's law. So the changing magnetic flux through a loop induces an electromotive force, EMF. So the induced EMF is the negative derivative of the magnetic flux over time. The magnetic flux in and of itself is the magnetic field times area times the cosine of the angle between the field and the orthogonal normal to the plane of surface that we're talking about or studying. Lenz's law, which is the induced current creates a magnetic field that opposes the change in the magnetic flux, is basically the negative sign of Faraday's law, or the reverse, negative reverse. Ohm's law relates to induced EMF, to current in the conductive tube. So I is the induced current, R is the resistivity, and E is the induced EMF. You can also rearrange it to find the resistivity and the induced current in it. Or it's already given in the induced current, but you can find the resistivity and the induced EMF this way as well, if given resistivity and the induced current already given. And then Savoy's law describes the magnetic field created in the induced current. So the derivative of B, which is just mu, the permeability of the free space, over 4 pi, then it's a derivative of the cross product of length times length times radius, and then radius over radius squared. As a result of the experiment, the magnet is flipped, its magnetic dipole reverses, which causes the induced currents to reverse direction. In the simulation, the red and blue colors switch, but the magnetic force still opposes the motion, so the magnet still falls down slowly. In real-world time in the tube may differ from the computational model because the simulation uses ideal assumptions like perfect rings, exact symmetry, and estimated magnetic values. Accuracy can improve by using better measured dimensions, a more accurate magnetic moment, and a smaller time step. The velocity versus time graph shows gravity speeding the magnet up at first, then induced magnetic force is slowing it down. As the upward magnetic force increases, the magnet approaches a nearly constant speed. So the process of coding this experiment was first creating the tube of aluminum foil, which you can see on the left. So you take the length, width, the inner radius. You take the radius with the width to get the overall radius, and it's the only thing was you take in the starter code and change those elements, and then creating the bar magnet. It was again filling in the magnitude that we saw from lab 3 in terms of the bar magnet when we did the induced dipole moment there. Calculating the magnetic flux, that was just taking the ring radius and then the distance, so the ring at the position y minus the magnetic ring at the position, and then the speed was just the magnetic velocity, which we calculated using Newton's first law or second law. And then motion prediction and visualization, that was already given in the starter code, basically how it's visualized in Python. So above, when the code is run, which I'll include in the abstract of this presentation, you can see the red bar falling a little bit faster than you would in the original, given the perfect conditions, as I mentioned before, and velocity versus time. The time in the tube, it's only 0.223 seconds, which in reality was not the case. So some errors could be inaccurate measurements of the tube length, radius, and the foil thickness, incorrect estimate of the magnet of the magnet's magnetic dipole moment, and all of these following reasons. So some discussion points is if the resistivity were induced as close as possible to zero, the induced currents would become larger because the tube would oppose changes in magnetic flux much more strongly. That would create a stronger upward magnetic force on the falling magnet, so the magnet would fall much more slowly and could approach a near floating or very low terminal speed motion. And then if holes or slots were cut into the tube, the ring currents would be reduced or broken entirely because the current would no longer be able to flow smoothly around the complete circular path. In the model, this would mean smaller induced currents in the affected rings, or even zero current if the slot completely interrupts the loop. So the magnet would experience less magnetic braking and would fall faster. And that is my presentation. Thank you for listening.